Yeah, so started recording. Fine. I'll now be starting the session. First, let me start sharing the screen. Ah, so I hope the screen is visible, right? I'm sure the screen is visible.
Yes, sir.
Yeah. All right. Okay. So as always, let me start with a quick introduction here. So this session here is a problem solving session for the course analog circuits. The course name is Analog Circuits. It's an NPTEL MOOC course, and the instructor for this course is Dr. Jayanta Mukherjee. He is a professor in IIT Bombay from the Department of Electrical Engineering. Myself, I am holding these problem solving sessions. My name is Mayank Anupam, and I'm a PhD student at IIT Kanpur. I also am from electrical engineering only. So today we will be discussing the contents that were covered in week 5 of the course analog circuit, and we'll be solving a couple of questions only today. So since the content was not much, okay, there was content wise this was a very I mean the content was very small. So today I will only be covering two questions to basically for this session. Okay, but before that I'll be quickly summarizing the concepts that were covered in this session in this week 5. Okay, so before that, let me ask you, do you have any particular doubt or anything in mind that you want me to discuss?
Yes, sir. Few in assignment 5.
Assignment 5, what is the problem? Okay, let
So
me.
basically, it was more of theoretical. So there were some questions which were not clear.
Okay, one second. Assignment 5 you want to talk about, right?
Yes.
Assignment 5, one second. Okay. So assignment 5 means week 5, right?
Yes, sir.
So is assignment 5 answers given? I don't think, right? Oh yeah, it is
It's
already
over.
given. Yeah,
Deadline.
yeah.
Deadline
It
is
is
over.
already due, right? Past due. So yeah, we can
Yes,
discuss it. So which question do you have a doubt in?
sir. 10th question
10th question.
and
Was
uh,
conjugation
sixth
pressure.
question also.
Sixth question.
Basically, I think
Yeah, you were
if
saying something.
possible, we would repeat it.
You were saying something. I was not able to hear it. Can you please
Okay,
repeat?
okay. I think you did explain that condition in a previous class.
Uh-huh.
But I didn't understood it much clearly, so I would like to you to repeat that. Question
Uh,
number 6.
Question number 6. I don't think I explained it.
Okay, okay, okay then.
Or maybe I did. I I don't remember. Okay, but I did say something about the gain about how gain affects the stability of the system.
Yeah, yeah,
I will
yeah. That's
again
it.
be I'll be talking about it again once today. So this is since this is assignment 5, right? It's something which has to be covered after week 5 content. So I'll first be
Okay,
covering. I'll be doing a recap. Okay, and then I'll be talking about it. Okay, please remind me
okay, sir.
again.
Okay, sir. About the assignment, right?
Yeah, about the assignment. Yes.
Okay, sir. Thank you, sir.
Yeah. Welcome. All right. So since only that, if that was the only question, then maybe I can start by doing a quick recap. Okay. And today's session will be short. Okay, I'll try to keep it short. I will try to finish it as soon as possible because I also have some work to do. And since there was not much content to be discussed in week 5, I think it should be done. It should be doable today. All right. So let me start by asking you. So did you guys understand what is meant by gain margin? I think I talked about it in the last class also, in the last session also. Gain margin.
Yeah.
Yeah, so this is pretty standard. I mean, there is a definition, right? Gain margin. And I don't think there should be any problem understanding what is gain margin. Okay. What I will try to do is I will try to explain you why gain margin is important and why do we talk about it. So definition wise, I don't think there should be any problem. Everyone understood what is the definition of gain margin, right? Okay. Mm, so let's start. I think I have a figure for this one in week 4. We have, okay, I don't have a figure. Anyway, no problem. So let's say I have a Bode plot like this. Hmm. And the phase plot for this would look something of this kind. So let's say this is the same omega axis, okay? And here you have, so you'll have start with 0, okay? And then you will reach minus 90 degrees and eventually you will reach 180 degrees. So this will look something of this kind. I mean 0 to it will reach 90 degree like this. Okay, and it will keep at this. Fine. Yeah, I mean this will asymptotically reach 90 degree. It will not 180. It will not fully reach 180 degree ever. It will be something of this kind. I mean, it will asymptotically reach 180 degree. It will never fully be able to reach this value, 180 degrees. So, in this figure, can you guys tell me what is the gain margin? How will I calculate what is the gain margin here?
At
Yeah, at what?
at omega p2.
At omega p2. Why omega p2?
Sorry, sir. At gain cross over frequency.
Gain margin is calculated at gain crossover frequency.
No, sir. Phase phase crossover frequency.
Yeah, so what is meant by phase crossover frequency?
Uh, the phase at frequency at which the phase of the system becomes minus 180 degrees.
Yes. So phase crossover frequency is what? Uh, Frequency at which phase of the system, or sorry, rather, loop gain becomes, sorry, transfer function becomes minus 180 degrees, right? That's what it is. So where does it reach minus 180 degrees in this case? Yeah, say something. Where does this
At
reach?
omega is equal to infinity.
Yes, exactly. So in this case, omega at omega equal to at omega tending to infinity, right? Your angle of h of j omega. So I have not written h of j omega. This is h of j omega mod in dB. Okay, and this is what angle of h of j omega. Fine, in degrees. So yeah. So in this case, there it tends to 180 degrees, minus 180 degrees, isn't it? So in this case, if you try to calculate the gain margin, you will say that the gain margin is equal to infinity, isn't it? Right?
Yes.
What is gain margin? Gain margin is equal to what? At phase crossover frequency, what is the gain? I mean, at this particular frequency, at phase, so what is gain margin? I think I wrote a formal definition also of gain margin. So tell me today, what is gain margin? It's
At phase crossover frequency,
at
what is the
phase.
gain required?
Okay, what is the gain required?
What is the what is the मतलब
Yeah,
how
yeah.
much frequency should be how much frequency should be increased to drive the system to the verge of instability?
Ah, no, 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 not that is not true. Gain margin is simply means that how much its gain is far away. Okay, I mean what is the gain of the system and how much is it far away from 0 dB. Okay, you are right, you are going in the right direction. So for system to become unstable, at what should happen? At phase crossover frequency, the gain should be equal to 1. Okay, if the gain of the system, let me write it so that it sticks in. So for a system to become unstable, the loop gain or its loop gain should be greater than equal to how much? 0 dB at phase crossover frequency. And just to uh, make it very precise, this whole statement is only true, or it's always true only for all pole system. Okay, if the system also has zeros, do you understand meaning of zeros, right? Zeros and poles. So if the system also has zeros, then this statement here, it can fail. Okay, so this statement is strictly true only when the system has only poles, it doesn't have a zero. Okay, fine. So so now what I was saying, yeah, so gain margin is what? It means that it is a margin. Gain margin means it represents a margin of how much, I mean it represents how much margin you have before you start becoming unstable in terms of gain. I mean if the gain becomes 0 dB, then you become unstable, right? So what gain margin means is that how much your gain is below 0 dB. Okay, that much is the margin that you have. So let's say your gain at at phase crossover frequency is minus 10 dB. Okay, in one case, and in another case, let's say your gain is minus 1 dB at phase crossover frequency. So what can you say about the two systems in terms of stability? Yeah, someone please. So one of you have said that a minus 1 is more stable. No, that is not true. You see, what did I explain? If a system's gain is close to 0 dB, or if it is equal to 0 dB at phase crossover frequency, then the system becomes unstable, right? It is more likely to become unstable if the system's gain is very close to 0 dB at phase crossover frequency. So what do I want? I want the system's gain to be as less as possible, right? As less as possible. So what is more less than minus 10 dB is much lesser than minus 1 dB, right? So that is why this is a more stable system. So that's why in this case gain margin is what? So tell me, in this particular case, what is the gain margin? Oh, by the way, again, at FPC, or rather at phase crossover frequency, it is equal. The gain margin is equal to what? I will represent it by GM. Gain margin is equal to minus of what? Minus of dB gain. Okay, of the system, of the loop. I mean dB gain of the system, of the transfer function. Okay. So what is meant by what is the gain margin here? Yeah, please say something. Otherwise, I'll just be moving forward, and I'll not know whether you understood it or not. So one of you are saying that it is nearly equal to zero gain margin. And what about other guys? What is your opinion on this? Come on, other people, please. Okay. So see, what you told, one of you have told is that it is very close to 0 dB. So that is, I mean, not not incorrect, I would say, but if you're talking, if you're strictly sticking to the definition, then it is incorrect. Okay, because definition wise, its phase crossover frequency is infinity, right? This system has a phase crossover frequency at infinity. So at infinity, what is the gain of the system? It is, I mean, you can see that, right? It is going so by the way, this is 0 dB line. Okay, so you can see that at infinity it is simply going to become minus infinity dB, right? So that is why if you talk about the gain margin here, the gain margin in this case is equal to infinity. Okay, but what you said is that is very, I mean, is not wrong. I would say that that is how it feels like, that the system's gain margin is very close to zero. It is because, and in fact, it is the case. It is actually very likely to become unstable very soon, because you see minus 180 degrees. Sorry, you can see that its gain becomes very close to, sorry, its phase becomes very close to minus 180 degree even when the gain is very high, right? So if you try to make a Nyquist plot of this, you will see that it is very, the system's the locus of point that it will cover goes very close to that critical point of minus 1 comma 0. Okay, it goes very close, and it is actually very close to instability. So yeah, so strictly speaking, its gain margin is infinity, but it is very close to instability. Fine. So gain margin, I think, yeah. So I was saying that what is the meaning of gain margin? Why do we talk about it? So if you remember in the last class, I said something about Nyquist plots and all. So I said that if you plot, if you make a Nyquist plot, there is a minus 1 comma 0 point here, okay, and this is sigma, this is j omega, and we used to plot our h of j omega here, okay. We used to plot our h of j omega, sorry, not h of j omega, but rather h of s here by varying s, okay, by varying s, and we used to get some plot, some random plot here, okay. So let's say this is the plot that we get. So we if you remember, I said that this guy here, uh, huh, this plot here, this plot here, it should not encircle minus 1 comma 0 point in a counterclockwise sense, right? That is what I said. If it encircles minus 1 comma 0 point in counterclockwise direction, then we have a problem, then the system is unstable, right? That is what I said. So let's see why this gain margin is used and what is the significance of it. Gain margin and phase margin both. So if you try to plot this system, this if we try to plot the Nyquist plot of this particular system, you see that there are two poles, right? Two poles of the system are there, and then the unity gain frequency here, it comes after the both the poles have hit, right? That is what the plot says to us. So let's make a Nyquist plot of this. So let's say it starts from some value, okay, then it starts going like this, okay, and 1 second. Oh, I think I made a mistake. It is not counterclockwise. It is clockwise only, okay? Clockwise sense. If this plot, if it encircles minus 1 comma 0 in the clockwise sense, then we have a problem, then the system becomes unstable. If it encircles in counterclockwise direction, then we do not have a problem. Okay, so please make a note of that. I think I made the same mistake week 4 here also. Let's see. I think I made a mistake here. I will correct it. The encirclement should be clockwise. Then we have a problem. If it encircles in a clockwise sense, then we have a problem. Fine. So let's try to do it. Yeah. If you try to make a plot of this one, you see both the poles have hit. Okay, both the poles have hit, and the gain is very high, even in that point. So if both the poles have hit, what is going to be the phase here? It is going to be very close to minus 180 degrees, right? So if you try to plot it, if you try to get a minus 180 degree phase here, how will you get it? You see this is 0 degree, right? This is minus something, minus this angle is how much? Minus 90 degrees, right? So if you go in this direction, you are increasing the angle to minus 120 or so, right? So where will be minus 180 degrees here? Yeah, where will be minus 180 degrees? Yes, where will be minus 180 degrees here? In which direction will minus 180 degree be? So it should be in this direction, right? This is minus 180 degree, isn't it? Fine. I hope you understood. Let's forget it. Yeah. So what it will do is it will go like this, and then it will gradually come to this point in this way, in this manner, and then the same will be repeated, and this is how it will do. Okay, this is going to be the Nyquist plot. So you see, it is actually going very close to minus 1 comma 0 point, right? Yeah. So I was saying, you can see here that in this case, oh, hmm. In this case, you can see that this one here is going very close to minus 1 comma 0 point, right? This plot here, it is going very close to minus 1 comma 0 point, something which you didn't want. If by chance, due to some mishappening, the system changes its behavior, and what happens is, let's say, instead of instead of this particular Nyquist plot, we get a Nyquist plot of this kind. Okay, if let's say that this happens, then we are in big trouble, right? If due to some reason, if the system changes its behavior and we get a plot in this manner, then what happens? You see, this minus 1 comma 0 point will be encircled here, right? It is encircled here and the system becomes unstable. So ideally, what do we want? We want our Nyquist plot to stay the hell away from minus 1 comma 0 as much as possible, isn't it? Isn't it? We want it to remain this whole plot. We want it to be as far from minus 1 comma 0 point as possible. So for that, for checking how far is it from minus 1 comma 0 point, we have two measures. The first one is phase margin, okay, and the second one is gain margin. So what is phase margin? What does phase margin means? It checks that when the, yeah, you tell me what is phase margin. You guys tell me what is phase margin and what does it check? Atharva. So you were saying something about phase margin, gain margin. Can you please say what is phase margin?
Sir, it is the measure of how much we are far away from minus 180 degrees.
Yeah, minus 180 degree at what point? When the frequency reaches, sorry, when the gain becomes 0 dB, right?
Yeah.
Yeah. So if you try to make a unit circle at minus 1 comma 0, so this is the picture. Make a unit circle here. Hmm. So in this case, what are we seeing? We are checking how much are we, I mean, when when our Nyquist plot, this Nyquist plot, its gain becomes 1 dB, so 0 dB, it becomes at this point, right? So at this point, we check what is, sorry, we check what is the angle at this point, right? And how much is it far away from this angle, right? Because for something, for this plot to encircle this point, the plot should, this angle will have to become 0, right? This angle will have to become 0, isn't it? So we just check how much angle we have left before we start becoming 0, start going close to 0 dB, right? So this is the angle that we talk about when we talk about phase margin, okay? And when we talk about gain margin, what is it that we are trying to see? We are trying to see that when it is going like this, when it is becoming minus 180 degree, what is the gain of the system at that point? Because if if it happens that the system becomes unstable, which happens when this encircles like this, right? In that case, you can see that at minus 180 degrees, so this picture is actually very cluttered now to look at. Let me use a different color which will be easy to visualize. Okay, so focus on the red curve. Okay, so let's say this is the new system. You can clearly see that. Let's say this is the new system, and this is the this thing. This is the Nyquist plot of the new system. You can clearly see that in this case, minus 1 comma 0 point, this point is clearly encircled, right? Clearly encircled by the plot. So you can see that when the phase reaches minus 180 degree, right, at this point, its gain is greater than 1 dB, 0 dB, right? Because this is the unit circle here. Okay, this is the unit circle, and and definitely this line here, this distance here is greater than 0 dB, right? Greater than magnitude 1. So that is why gain margin here is becoming what? Is becoming negative. Okay, because gain margin was what? Gain margin is negative of dB gain of the system at phase crossover frequency. So in this case, the dB gain of the system is positive, right? It's greater than 0 dB. Negative of this will become negative, right? That is why the gain margin here is negative, which means that the system is unstable. Okay, so I hope you understood what is the meaning of gain margin, phase margin. Why do we talk about it when we talk about stability? So you guys have any doubt in that?
सर वो गेन मार्जिन का 1/mod ऑफ वो ट्रांसफर फंक्शन मतलब फंक्शन लेते थे ना सर, वो वाला क्या था सर?
हाँ, तो वही तो किया है, डी माइनस ऑफ गेन इन डी वी किया ना। ये इसका मतलब क्या होता है, आप इसको अगर आप मैग्नीट्यूड में लिखिएगा, गेन मार्जिन इज इक्वल टू 1 ओवर मैग्नीट्यूड ऑफ एच ऑफ जे ओमेगा। ओके, ये होता है। और जब इसको आप डीबी में कन्वर्ट कीजिएगा तो क्या बनेगा, आप डीबी लीजिएगा ना, लॉग ऑफ समथिंग, लॉग ऑफ 10, 20 लॉग ऑफ 10,
माइनस
राइट? तो
माइनस
माइनस आ जाएगा ना,
यार ओके
आ जाएगा ना, राइट? सो वही वही किया है यहाँ पे। एनीवे, सो दिस यू अंडरस्टूड, राइट? Now, now let's move forward. Did you guys understand what is this frequency compensation and what is the meaning of that? Frequency compensation. If you don't say anything, I'll assume that you have understood it. Did you guys understand what is frequency compensation?
Sir, in this we are trying to make that minus 20 decibel per decade. We are trying to expand that region.
Yeah, correct. So why do we try to expand this region? I mean,
Sir,
there is
because we are literally far away from minus 180 degree,
correct. So
and
see,
we
yeah, exactly, yes. So it's exactly what everything you can visualize using looking at this plot, right? Nyquist plot. So if your phase is only minus 90 degrees, so see, minus 20 dB per decade means what? You have hit only one pole, right? Only one pole in the system, correct? And one pole means you are only in this region, minus 90 degrees, isn't it? One pole means your
yes,
phase will be minus 90 degrees, right? Which means that in your Nyquist plot, what will happen? You will go something of this kind, and then you will reach this like this, something of this kind. So you will do this and you will reach this point like this. So you are very far away from minus 1 comma 0 point, right?
yes,
Yeah. So that's why we talk about frequency compensation. We want to make sure that our loop gain, it rolls off at minus 20 dB per decade slope, right? It rolls off around which point? Around the point where the gain becomes equal to 0 dB, or gain crossover frequency, right? We want to make sure that happens. Understood? So for that we do all kinds of compensation. So do we require a compensation in this circuit here, in this particular transfer function? Should we do a compensation here?
No, sir. Like if we
Why
see
not?
the region,
Huh? Come again?
सर वो बीच वाला रीजन -20 डेसिबल पर डिकेड वाला थोड़ा मतलब इट्स ऑलरेडी एक्सपांडेड ऐसे लगा
नहीं
कर
बट
सकते हैं सर लाइक
नहीं
वी
करना
कैन डू
चाहिए
इट
या नहीं, करना चाहिए या नहीं?
करना
Why do
चाहिए
we,
सर
क्यों करना चाहिए?
बिकॉज़ विल गेट बेटर फेज मार्जिन राइट सर
Yeah, because you see in this case it is very much necessary, right? You see this the phase margin is very poor here, isn't it? आपको you see in this case I have not drawn it very well, but actual figure if you try to make actually, so if you try to make an actual plot of this particular this particular this thing, it will look something of this kind. Okay, you see phase margin is very poor here. At this point becomes equal to uh, gain becomes equal to 1, right? And here at this point you can clearly see, the angle is not very large, isn't it? The margin is phase of the phase margin is very poor at this point, isn't it? So you want it to, I mean you can see from the plot also that this Nyquist plot here, it goes very close to -1 comma 0 point, isn't it? You don't want that. So you definitely want it to become to be compensated. And from the Bode plot also you can see, as I just said about it, you want at the gain crossover frequency, okay, around the gain crossover frequency, I mean near that region where the gain becomes equal to 0 dB, you want the slope of the transfer function to be 20 dB per decade. Okay, you don't want it to be higher than that. Are you getting my point, Ganesh?
yes sir
Yeah, so that is why in this case it is actually required for you to compensate it. So what should you do to compensate this particular network? What are the tools that you have learned to compensate?
सर कैपेसिटर
You want to add capacitor, but that is the final implementation. I am talking about idea wise. What are the two ideas that you learned, right? There were two ideas and they are written here. So I wanted the names from you. It's okay, fine. It's written here. So first one is dominant pole compensation, right? This actually this name was not mentioned. So it's okay if you are not able to name it. Dominant pole compensation means exactly the same thing that you are talking about. It means you add a capacitor somewhere, so that in this case what happens is you make sure that this pole here, this is the dominant pole, right? This is the dominant pole,
यस
isn't
सर
it? So you make sure that this dominant pole goes back further, which means that this will start rolling off from very early on, like in this case let's say it starts rolling off here and it will keep going like this, or in this case let's say it does it even further, even from behind like this. So before it hits the next pole, I mean you understand the idea, right? The figure I have not drawn it very well, but you understand the idea that it will start rolling
यस
off and then it will simply go like this, and the second pole will hit after the unity gain frequency omega u here, right? So in this case the pole is now new pole is where, at this point omega p1 dash, this is the new pole location, correct? So this is where,
यस सर
this is how you do it. In this case you have not touched, you have not affected the location of the second pole, okay, all other poles. You have not affected the location of the non-dominant poles. You have only affected the location of the dominant pole, right? This is the dominant pole here. You have only affected the location of the dominant pole. You have made sure that it shifts even backwards. So this is dominant pole compensation. And the other idea is what? Miller compensation, right? What do we do in Miller compensation? What do we do in Miller compensation? What do we do in Miller compensation?
Sir, will you explain that one, Miller
Yeah,
compensation?
okay, fine, fine. So you see, in the dominant pole compensation, we simply made sure that the dominant pole moves backwards, right? We didn't touch the non-dominant poles, isn't it? So what was the
Yes,
problem with this idea? It reduces the effective bandwidth, isn't it? The
yes, sir.
bandwidth reduces here. So some genius people, they figured out a way to make sure that the system becomes stable or the phase margin increases without affecting the bandwidth of the system very much. Okay, you see, in this case, in the dominant pole compensation, bandwidth reduces a lot, isn't it?
सर मतलब वो बैंडविड्थ जो होता है ना सर वो 0 to ω u तक होता है ना सर आई
हाँ,
मीन
ऐसा कुछ समझ
हाँ
लो,
वो
हाँ, करेक्ट।
तो वो मतलब रेड्यूस होके जो ओमेगा यू है पीछे आ जाता है राइट सर वो
बहुत पीछे आ जाता है, हाँ
मतलब
करेक्ट।
पिछले वाले टेक्निक में
हाँ करेक्ट, बहुत पीछे आ जाता है ओमेगा यू। यस,
हाँ तो वी आर
करेक्ट।
ट्राइंग टू कीप इट एट ओमेगा यू लाइक एट द सेम लोकेशन और व्हाट्स इन दिस वन
Yeah, same location, or it will move slightly. It will move only slightly. Okay, it should not be moved as much. You get the idea?
या या
Yeah. So this is what some smart people figured out a way to do it. So what they did is they used the idea of Miller. I mean Miller theorem. Miller's theorem. So what Miller's theorem? You already saw it, right? If you add a capacitor, if you do it, if you take a voltage controlled voltage source of gain A, if you add a capacitor across this, right, if you do it, see, so what is the capacitance that you feel from this, looking from this side? Sorry, this is minus A, by the way.
1 plus 8 times of 1
Yeah,
minus 8 times of
no, it is 1 plus A
okay
in this case,
8 times
right? Correct.
yeah yeah
So looking from this side, you feel that the capacitance has increased by the gain of the amplifier, right? Isn't it?
yes sir
Yeah, so this is what some genius people figured out. What they did is, generally what you do in the feed, this is generally used in feedback only. So in the feedback of some stage, what people did is they added a capacitor across it. Okay, like in the module also you saw how they, how to do this, right? In this particular situation like this, right? This was the capacitor. You added it between these two terminals, isn't it? And we know that the this MOSFET, it behaves like a amplifier, isn't it? From input to output. If you don't know, it's okay. I take my word for it. It behaves like an amplifier from input to output. This is the input here. This is the output here. So it behaves like an amplifier of some gain between input to output. So what will happen? It will feel like at the, looking from this side. From this side, it will feel like the capacitance is not Cc, but rather it is Cc into some factor, right?
yes sir
Yeah. So because from this side, if you work out, and it was also shown in the module, okay, that from looking from this side, it will feel that the overall transconductance is amplified. From looking from this side, if you write, so tell me something, what is the general form of a pole? It is some G, some conductance over some capacitance, right? Some G over some C, right? This is some pole. The form of the pole is something of this kind, isn't it? It should be some conductance over some capacitance, correct?
yes sir
Yeah. So in looking from this side, okay, and by the way, when I say from this side, this was supposed to be the dominant pole location, okay. This was earlier, before adding this capacitance also, this was acting like a dominant pole, this node here, okay. So what did you want? And to make sure that the pole to make sure that the system is stable, you wanted to make sure that the uh, that this pole here, this pole which appears at this node here, moves backwards, right? And how will you do that? Pole becomes less when the pole frequency reduces, when
Increase the
capacitance
capacitance.
increases. Yes. So that is why you added a capacitance here, which means that when you add this capacitance, the overall capacitance simply increases, right? Simply becomes very, very large because it is amplified by the gain of this amplifier, right? And looking from this side, now what the problem with dominant pole compensation was, what? The omega u was also moving back, right?
Yes, sir.
But that you didn't want. So if you work out, you will see that that doesn't happen because the second pole here, the second pole which appears here, okay, that moves away. Away means that increases in value. And how is that achieved? That is achieved because this capacitor Cc, it results in overall increasing of this conductance which appears at this node, at the output node, okay. Because of that, in one side, so if you try to look at the frequency axis, let's say earlier your omega p2 was at this point and omega p1 was at this point without adding this capacitor, okay. What will happen is, because of this capacitor, uh, something happened, okay, sorry for that. Yeah, I was saying, because of this capacitor, what will happen, this pole here, it will move even further, it will go somewhere here, and this pole here, it will also move further, it will go somewhere here. You get the idea? And the overall this thing, your, let's say your earlier uh, unity gain frequency was here, so it will maybe move only this much and it will remain here only, okay, compared to the case where you had to move it to somewhere around this point. You get the idea?
सर जी लाइक दैट वो जो इनपुट वाला कैपेसिटेंस है
हाँ
at 1 plus a times of c,
हाँ
I know that will move this dominant pole omega p1 towards left side, right?
या
हाँ, तो लाइक ये ओमेगा p2 जो और एक पोल है ना सर वो,
हाँ हाँ
so that will move towards right. Is that because of input capacitance or because of the output capacitance?
you see
That output पे
this is,
capacitance reduce होता है ना सर?
yeah, understand output पे capacitance reduce नहीं होता, आउटपुट पे
सर लाइक
कैपेसिटेंस,
वहाँ पे 1 + 1/a times of c आता है ना सर?
हाँ तो 1 + 1/a टाइम्स सी होता है ना, रिड्यूस तो नहीं हुआ, 1 + 1/a
Reduce,
टाइम्स सी
हाँ,
is very close to C. It is not
yeah,
reduced.
yeah, yes. Okay,
Yeah,
okay.
it is actually that much only. But you see that at the output there is always going to be a load capacitance CL, okay? And this CC is going to be much less than this CL. So don't worry about it. Overall, the pole at this node is going to be dominated by the CL in terms of capacitance, okay? So the only way to increase the pole location, to increase the frequency of this particular pole, is to make sure that the overall conductance at this node increases, okay. You get the idea?
Yes.
हाँ, the conductance it
Sir, I had another
हाँ
doubt.
हाँ बोलो.
Sir, like the small signal model of this, let's say amplifier and MOSFET, are they both same or quite different?
And this MOSFET is ideally a voltage controlled current source, okay. It's a VCCS, it's not a VCVS, whereas this is VCVS, okay. So Miller's
Yes.
theorem, or rather this one, this particular effect which you see, is strictly applicable only for VCVS, that too ideal VCVS, okay. It is not applicable for VCCS. However, this VCCS, if you add a load here, if you add a load which is like this, resistor like this here, so it will start behaving like a VCVS. Okay, and there are some a lot of
Yes.
conditions applied in this particular statement. However, those conditions are beyond the scope of this particular whole course. Okay, not just this week, but but the whole course. So I'll not be talking a lot about it. Just take my word for it. You'll learn about it when you go and take a higher level course. Fine. Also,
Yes.
the reason the way how how this capacitance helps in increasing the overall conductance at this node. Also, that is also beyond the scope of this particular course. So again, take my word for it. If you want, you can work it out. But I'll not be discussing this. Okay. Yeah. But you just keep in mind that a Miller capacitance, this idea of adding capacitance between the input and output of an amplifier, it is used to make sure that the system is compensated. Okay.
Yes.
Yeah. So if that is done, in that case, I'll just be yeah. Filters was just introduced here, so I will talk more about it in the next session. Okay. I'll not talk about it today because it was just introduced, and I think most of you understood the introduction part. There was nothing much to understand there. Introduction was fairly simple. It was just about the definition of the different kinds of filters. Okay, so this is fine. If that is all, I'll then be going on to the questions that I wanted to discuss today. Uh, yeah, but before that, the question that you asked me about this question, right? Sixth one, isn't it? Did you ask the sixth question, Ganesh, or was it someone else?
So someone else.
Okay. Anyway, so if the I'll just discuss it if that guy joins. It's okay. Otherwise, he'll just watch on the YouTube this thing. So fine. If the gain of the open loop system is double, the gain margin is what? So you guys tell me. Oh, it is already answered here, so doesn't matter. If the gain of the open loop system is doubled, the gain margin is affected or not. So what do you think? I mean, the answer is given, but let's convince ourselves that whether this is the answer or not. So tell me here, looking at this example, what will happen? Oh, this is not a very good example. Okay. Hmm. So how will the plot look like? Phase plot. So it should be like this. Uh, Oh, I think I made a mistake. Hmm. Hmm. It will look something of this kind. Okay. So this is going to be minus 45 degrees and this is going to be minus 135 degrees. All right. So in this case, again, tell me what is going to be the phase gain margin. Okay, so let's also do this. Uh, no, this is not again a good example. Yes, so in this case, this will look something of this kind. So there are three poles, okay. So its phase should reach up to minus 270 degrees, okay, at omega is equal to infinity. So in this case, tell me what is the gain margin? How much from the figure? Where does it look like? How much it should be? Gain margin. What should you check for gain margin? Yeah, someone wanted to
Sir,
say something. Yeah, Ganesh. Yes.
sir, we'll calculate actually the length between at
Yeah,
minus 180 degrees,
correct.
right, sir?
So yeah,
The
so
length
so
from the
you hit minus
frequency
180
axis
at this
to
point, right? You hit minus 180 at this point. So you have to so this is the point where you hit minus 180. So you drop a line like this, correct? Isn't it? A line like this, and then you see. So at this frequency, what is the gain? So this is the gain, right? Right. So this is the
yes,
and you have to see how much. So this is basically the gain margin in terms of dB. This distance here, this distance here, it's the gain margin in terms of dB, right?
yes,
So dB of this is gain margin, correct? So this is the gain margin. Now tell me something. If you increase the gain by 2 times, how will this affect the overall gain margin? So what will happen if you increase the gain? What should happen to this? Should go up, right?
yes, sir.
The overall plot should shift up, isn't it? Everything. Correct. So in that case, what happens to omega u here? It should go forward. It should move in the right direction, right? In the in this direction by 2 times. Correct. Am I right?
Yes.
Correct. This should move in this direction by 2 times. So, but omega p1, this one, and omega p2 and p3, all of these, they will remain unchanged, right? Because you have only scaled the system, the gain only is increased, but the overall the pole locations have not changed. So only omega u will change, but omega p1, p2 and p3 will remain unchanged. Correct? Am I right?
Yes.
Yes. So tell me something. If omega p1, p2 and p3 remain unchanged, and so will the phase plot be affected? Will this phase plot, will it be affected if omega p1, p2 and p3 have not changed? Will the phase plot be affected?
It won't be affected.
It won't be affected. So if the phase plot is not affected, then the place where the frequency at which the phase reaches minus 180 degree, that also shouldn't be affected, right? It should remain same.
Yes, sir.
Good. Now if it remains the same, but I have already said that the gain should increase by 2 times, right? Overall, I mean the plot should move up in the upward direction. Or the overall plot will move in the upward direction, and how much will that move? 6 dBs up, right? It will move 6 dBs.
Yes.
So tell me, will the gain margin be affected or not? Will this distance be affected or not? Should this distance be affected or not?
It will be affected, sir.
It should be affected, right?
Yes, sir.
Yeah, so what should happen? Should the gain margin decrease or increase?
Gain margin should decrease.
Yeah, it should decrease, right? So
Yes, sir.
GM should decrease, isn't it? Am I right? Gain margin should
Yes.
decrease. Am I correct?
Yes, sir.
Hmm. So what the answer that you have here, it is incorrect. Where's the answer? Not affected. It doesn't look
Yes, sir.
correct to me.
Not
S-
affected.
Yeah, it shouldn't be. It looks wrong to me. The answer is wrong here. It should be affected. It should become what? Gain margin should be
Half.
halved. Yes, it is incorrect. The answer. Fine. The next question is, which of the following causes change in gain and phase shift? Tell me. What are the options? Internally integrated resistor, internally integrated
The
inductors,
capacity.
internally integrated capacitor, both B and C. Which of the following causes change in gain and phase shift? What do you think?
Sir, capacitor. Like,
And why not inductors?
sir, I, matlab, you taught us with capacitors, right? Sorry, that frequency compensation and all.
I did, but you see, both inductors and capacitors can cause gain and phase shift. Okay,
Yes.
yeah. So again, this also doesn't look correct to me. It should be both B and C, but I don't know what they
Yes.
have done. So maybe they were looking for answers which only have been covered in the class. So inductors also can be used to compensate, just like capacitors. Okay, inductors are also used. They can also be used. I mean, the question is very straightforward. It is asking whether what can be changed, used to change the gain and phase shift. So that also can be done by capacitor inductors, just like capacitors. Anyway, so let me talk about the questions here. The transfer function of a system is given as g of s. The system is placed in a unity and negative feedback as shown. So calculate the phase crossover frequency of this system. Quickly, tell me, what will the phase crossover frequency of this system? So g of s is given, right? So what is the loop gain? What is going to be the loop gain?
G of s into 1.
Yeah, correct. It is g of s into 1.
So like I had a doubt.
Huh?
Uh, this we in this control system we have this closed loop gain and like overall one is open loop gain, sir.
Uh-huh.
And the one which you wrote, the loop gain is g of s into the one which is having feedback.
Yes.
And the overall gains, that would be something like g of s divided by
1 plus g of
1 plus g
yeah.
of s into that, right, sir?
Yes, yes, yes.
Okay. Thank
Yes.
you.
Yeah. So a lot of people actually differentiate between open loop gain and closed loop gain and lot of other things. So I am when I write loop gain, I mean the overall the gain that is in this loop. Okay, that is what I am talking about. Fine. So this is g of s into 1. So what is that? It is 10 divided by s into s plus 100 the whole square. Correct. So what is the phase crossover frequency for this one? You have to equate the phase to minus 180 degrees, right? Correct. So you know that at phase crossover frequency. Hello, am I audible?
Yes, sir.
Yeah, at phase crossover frequency, we have what angle of g of h of g of omega j omega has to be equal to minus 180 degrees. Correct. Fine. So yeah, not g of omega, but rather L of j omega. So by L I mean this is L of s. Okay, loop gain. This is L of s. So this is the L of j omega. So what we have to do is we have to replace L of s with s is equal to j omega. So that is equal to 10 upon j omega into j omega plus 100 the whole square, right? And then we have to find the angle of this angle of L of j omega. So what is this? So this is minus 90 degrees, right? J omega is what? Minus 90 degrees, isn't it? Is there any doubt in this? This is minus 90
No, sir.
degrees minus 2 tan inverse of how much? Omega upon 100, right?
Omega by 100.
Correct? Fine. And phase crossover frequency, this has to become equal to minus 180 degrees, right? This is also fine. So this gives us what? This gives us 90 degrees should be equal to what? 2 tan inverse omega upon 100. And we know that 90 by 2 is 45 degrees and tan of that is 1, right? 1 equal to omega by 100. So what is omega? 100 radian per second, right? Yeah,
Sir,
this is fine. Tell me.
sir, like instead of this, if we had a question like 10 by s square and s plus 100 into s plus 100, like what would you put in phase margin instead of s square?
Come again.
Sir, like instead of this g of s, if you are given like 10 by s square, 10 upon s, s plus 100, like
So what?
what would be the phase margin, like the equation?
Oh, what do you think? The phase, due to the s square, what is going to happen? Minus
Yeah, like
180 degrees, right? So it is minus 2 into 90 degrees, right?
okay, sir. Yes, I,
You're not audible, Ganesh. I'm not able
I
to
got, sir.
hear you.
I got
Yeah. So this is at plus what? Minus tan inverse, or rather minus
tan
tan
inverse
inverse
of
of
omega by 100.
omega by 100, right?
Yeah,
This is
yeah,
the
yeah, it's
situation.
I got.
Hmm. And by the way, in if you have a transfer function of this kind, what do you think about the instability? Sorry, stability of the system? Yeah, Ganesh. What do you think about the stability of the system if you have a transfer function of the kind that you just suggested?
It would be unstable, sir, but like
It,
it would
it
reach
would
minus
be,
180-degree faster,
yeah,
right?
correct. So it is very close to instability. So say such a system you have to be, uh, you have to compensate such a system. Okay.
Yes.
Even in this case, you see phase crossover frequency. Even this particular case here, this is not a very good system. But since the gain was very less here, 10, so the system is stable. If you calculate the phase margin, you will see that this system is very well stable. But this system here, it is not going to be stable. Fine. So that's done. Now calculate the gain margin. So what is the gain margin? So we have already calculated the phase crossover frequency, isn't it? So gain margin should be a piece of cake now. So what is gain margin? So first, what is the gain at phase crossover frequency? What is the gain at phase crossover frequency? It is mod of L of j omega at omega equal to omega pc. Okay, what is that? This is the right, or rather this one. So it is 10 upon j times, or if you are only talking about modulus, right? So 10 by omega which is 100, 10 by 100 into j omega plus 100, which is how much? Omega square plus 100 the whole square, and then square root of this, correct? And the overall whole square, right? So it will be, the square and square root will go away, so it is this much. So what is this? 10 by 100 into 100 the whole square, 100 square plus 100 square. So how much is that? 2 into 100 square. So 10 divided by 100 cube into 2, which is how much? 10 to the power of how much? Minus 5, right? Into 0.5. So what is it in terms of dB gain? What is the value in terms of dB?
सर वो 106 कुछ है minus,
Huh? So it is
like
minus 20
overall
log of, it is
minus
minus 20 log of 10 to the power minus 5
uh, 10 to the power
minus
minus
20
5,
log of
20 log of
0.5, correct?
5. Yes.
And what is this? This is 25 is 100, right? Plus 6, correct?
Yes.
Almost 6, I mean 6 point something, so it should be 6. So it is 106 dB, right? So the gain
Yes.
margin is very high here. So the system is very, very stable. Okay?
Sir, like in this one,
Huh?
like यू मतलब आपने 20 लॉग सीधा ही लूप गेन के लिए ही लगा दिया ना सर?
हाँ
हाँ तो फिर वो ओवरऑल गेन के लिए लगाना पड़ेगा ना सर हमें, दैट
मतलब
1/h ऑफ j ओमेगा, आई मीन,
हाँ
तो उसके लिए
हाँ
लगाना पड़ेगा ना सर, तो
हाँ तो
उसमें तो
1/,
-106।
नहीं 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 नहीं, तो इसलिए तो यहाँ माइनस लिया है, राइट, यहाँ माइनस लिया है। एक्चुअली लॉग डीबी में कन्वर्ट करने के लिए माइनस नहीं रखता ना, यहाँ पे प्लस होता है ये। मैंने माइनस लगाया क्योंकि 1/, ये था, राइट, 1/, ये 1/, ये, इजंट इट?
सर मतलब लाइक ये गेन मार्जिन कैलकुलेट करने के लिए भी हम लूप गेन ही यूज करते क्या?
गेन मार्जिन कैलकुलेट करने के लिए हम लोग लूप गेन यूज करते हैं, लूप गेन का 1/, लूप गेन यूज करते हैं, ओके। इट इज एक्चुअली 20 लॉग ऑफ 1/, लूप गेन, एल ऑफ जे ओमेगा, ओके।
यस।
लेकिन व्हाट व्हाट विल दिस बिकम? अगर आप इसको लिखिएगा तो क्या बनेगा, ये
-20
माइनस
लॉग
20 लॉग
ऑफ
एल ऑफ जी ओमेगा, राइट। तो वही मैंने किया
सर
यहाँ पे
देन,
-20, यहाँ पे -20 कर
सर
दिया
देन
पहले ही।
वो ओवरऑल गेन का कुछ क्या सिग्निफिकेंस है सर, लाइक वी यूज इट और वी वोंट यूज इट?
This is the overall gain, isn't it? The L of j omega. This is overall loop gain. What do you mean by overall gain? What gain are you talking about?
लाइक आई मीन सर वो a/1 + a टाइम्स ऑफ बीटा आता है ना सर,
Oh,
जब
closed
बीटा
system
फीडबैक
gain.
होता है।
Closed system
या
gain.
सर,
Okay,
तो
that
आई
is
हैड अ
that is
कंफ्यूजन इन दैट वन।
yeah. So that is required when you want to calculate the overall system's transfer function. I mean, if you want to find out the transfer function between y and x here, okay, then you need that closed system this thing. Otherwise, you don't need it.
सर लाइक could you please give me a clarity between this overall and this one sir?
I mean, what kind of
जो
clarity? I mean, this is very clear.
लाइक
Loop
जो
gain is
y
the
by x
हाँ
loop gain is g of s into feedback,
yes.
and the y by x is that one is closed loop gain sir.
Closed system gain, yes. Closed loop gain, yes.
Yes, thank you.
No, no, but some people use closed loop gain for the loop gain itself. Okay, please, so you see, this is my terminology. Don't stick with it. Some people, some standard texts have used closed loop gain to mean the loop gain only. Okay, you
Yes,
understand what I'm trying to say? Some people use closed loop gain to mean the loop gain itself. When I say closed loop gain, I mean the overall this thing, the transfer function between the output and input in the closed system, closed loop system.
yes.
Okay, yeah, fine. Yeah, the transfer function of a system is given as g of s. So this system is placed in unity and negative feedback shown problem 1. The same figure, okay, that we had. You have this x, okay, and then you have g of s, then you have y, and you have this particular scenario. Sorry. Okay, this is the situation. Now this is the g of s. Calculate the gain crossover frequency here. Tell me, how will you do it? What is the gain crossover frequency here?
सर लॉग लगा के 0 पे इक्वेट कर।
Yes. So solution. What do you do?
We can even equate it to 1 and try
Yeah, that is
solving
what
for.
you're doing. Yes. So the loop gain is going to be g of s into 1, right? So what do we do? And this is equal to L of s. So we have to equate L of j of omega to 1, isn't it? Correct? At gain crossover frequency. All right. So this becomes 100 by j omega into j omega plus 10. and magnitude of this should be equal to 1. Alright, so how much will this be? 100 upon omega into omega square plus 10 or 100 under root of this is equal to 1. So here we can make an approximation. Okay, this is very crucial. Please pay attention to this. This is generally done when you try to calculate the gain crossover frequency. We assume, sorry, we assume for time being that assume that at gain crossover frequency, the omega gain crossover frequency, let's call it omega u. Okay, at gain crossover frequency omega u, or rather assume that gain crossover frequency omega u is much greater than 10. Okay, so do you understand this assumption? I'm just assuming that the gain crossover frequency omega u is much greater than 10. Why 10? Because there are two frequencies, by the way, here, two poles, right? How many poles are there in this particular transfer function? Two poles. And what are those two poles? Tell me.
0 and minus 10.
0 and minus 10. Correct. So what I am doing is I am assuming for time being that uh, at the gain crossover frequency omega u, sorry, the gain crossover frequency omega u is much greater than both of these two. Okay, I am assuming that for time being. Let's see what happens. So if I assume this particular scenario case, and by the way, if this assumption will verify later whether this assumption is true or not. If this assumption stands out to be true when we calculate omega u after using this assumption approximation, okay, if we find out that omega u is indeed much greater than 10, then we will be happy and will not do anything. If it turns out after calculating that omega u is not very greater than 10, then we'll have to do something else. We'll have to come back and then redo the stuff because this assumption didn't hold. So let's see what happens. Because of this assumption, now what I can do is this is 100 divided by omega into, since omega is much greater than 10, so omega square is also much greater than 10, 100, right? So what I can do is I can approximate omega square plus 100 simply omega square, right? I can do that. And by the way, here j omega, it is omega u. Is this understood? Is this okay?
Yes, sir.
Yeah, fine. So what will this give me? 100 upon omega u square is equal to 1, right? So omega u square is equal to 100. This gives me omega u is equal to 10, right? 10 radian per second. Correct? So now tell me, is this value of omega u much greater than 10? I mean, does the assumption hold? Does the initial assumption that we made?
No.
Yeah, it doesn't hold, right? So our assumption failed. So assumption failed. So we'll have to do the whole thing, right? Let's say that our assumption didn't fail, and let's say in this case after calculating omega u turned out to be, let's say, 100. Okay, then we wouldn't have to do anything else. Omega u would equal to 100 would be the correct answer. Okay, it will be very close to the correct answer. Since in this case the assumption failed, so we have to do it again. So let's go back and do it again. So this is omega u, right? This is here. So let's take a square both sides. So this is 100 the whole square divided by omega u square into omega u square plus 100 is equal to 1. And then, okay, so this is not good. So this will give me what? This will give me 100 square equal to 110 to the power 4 equal to omega u to the power 4 plus 100 omega u the square. So this gives me omega u to the power 4 plus 100 omega u square plus minus 10 to the power 4 equal to 0. This gives me what? Minus of, this gives me omega u equals of omega square equals minus 100 plus minus under root how much? 10 to the power 4, right? Minus 4 into 10 to the power 4 plus 10 to the power 4 divided by 2, right?
Yes.
Yeah. So tell me, there is a plus and minus, right? So which one should I keep and which one should I not keep?
The one which is positive.
Yes. Why is that the case?
So like bandwidth is always positive, right? So like 0 to, let's say for
Even
an op amp it is 0 to
no
5 megahertz
no
and all.
even more important, omega u's has to be real, right? It has to be a real number.
Yeah, yes.
Yeah, and you see that omega u square is equal to this guy, correct? So if omega u square is equal to this, and if omega u is real, then the square of a real number is always positive, isn't it? So that is
Yes.
why, it has to be plus 100 plus root over 10 to the power 4 plus 4 into 10 to the power 4 divided by 2, which gives me how much? It is
Root 5 minus 1 into
yeah,
100
correct.
divided by
So it is 100 into root 5 minus 1 divided by 2, correct? So it is 50 into root 5 minus 1. When you take so what is the value of omega u? Omega u will be again root over 50 into root 5 minus 1 1 over 2. Again it will be not plus and minus, it will simply be plus, because as you said correctly, the bandwidth has to be a positive number. Omega u has to be a positive number because it's frequency, so it has to be a positive number. Fine. So this is our omega u, gain crossover frequency. And what is the phase margin? So put this value of omega u in the equation for phase margin that I gave in the last session. You will get the phase margin. And yeah, so after that you have to do all this stuff. So if the phase margin is changed to 60 degrees, in this question there is a catch. Okay, the question is, once you calculate phase margin, you see there's the phase margin is some value. Okay, it will definitely be very poor. And when you calculate phase margin, now the question is, if the phase margin of the system is changed to 60 degrees, calculate its new gain crossover frequency. Okay, that you have to calculate. So how will you change the phase margin? By the way, the system is very it has simply given the question that the phase margin of the system is changed to 60 degrees. So how will you change the system's phase margin? What should you change to change the system's phase margin to 60 degrees? Tell me.
सर वो ओमेगा गेन क्रॉस और फ्रीक्वेंसी को चेंज करना पड़ेगा ना सर? तो
हाँ, गेन कॉन्स्टेंट फ्रीक्वेंसी चेंज करना पड़ेगा। कैसे चेंज करेंगे आप? क्या क्या
तो वो
तरीके से चेंज
आपने
करेंगे?
सीखा आपने सीखा सर मिलर कॉम्पेंसेशन.
हाँ राइट, तो वो तो ठीक है। सिस्टम लेवल पे क्या चेंज करेंगे? इस 100 को रिड्यूस कर सकते हैं, राइट? रिड्यूस या इंक्रीज जो भी हो, इस 100 को, मतलब ये जो डीसी गेन है इसको चेंज कर सकते हैं, राइट? अभी हम लोगों ने वो क्वेश्चन देखा था मल्टीपल चॉइस कि अगर सिस्टम के डीसी गेन को चेंज करते हैं तो गेन मार्जिन चेंज होता है या नहीं, करेक्ट? सिमिलरली फेज मार्जिन भी चेंज होता है।
यस.
तो अगर सिस्टम के डीसी गेन को चेंज करेंगे तो फेज मार्जिन गेन मार्जिन दोनों चेंज होगा। ओके,
यस.
हाँ, दूसरा एक और तरीका ये भी है कि अगर आप इस 10 को बढ़ा दें, राइट, 10 को अगर बढ़ा दें आप, क्योंकि एक पोल तो 0 पे है, इसका कुछ नहीं कर सकते, राइट, लेकिन जो दूसरा पोल 10 पे है, -10 पे है, उसको छेड़ सकते हैं हम लोग. वी कैन चेंज दिस पोल, राइट, वी कैन चेंज दिस पोल. वी कैन, if we increase the value of frequency corresponding to this pole, then we can also increase the phase margin, right?
Yes, sir. Sir, but वो आपने जो previous question में
Okay,
that
I'm not able to hear
not
you.
affected. Hello.
Yeah, you were saying something, Ganesh?
हाँ सर, वो previous question में जहाँ पे आपने not affected का वो problem बताया था ना सर,
हाँ,
तो वहाँ पे तो phase change ही नहीं हो रहा था ना सर, phase पे कुछ
फेज
effect ही नहीं
मार्जिन
पड़ रहा.
चेंज हो जाएगा ना, लेकिन द फेज मार्जिन विल
हाँ हाँ,
डेफिनेटली चेंज,
yes sir,
इजंट इट?
okay okay.
Phase
Right.
will not change, phase margin can change because phase margin is a function of omega u also.
Omega u. Yes sir.
Correct. So यहाँ पे we have two handles, right? One handle is to change the gain, right? To change the gain of the system, that will change the phase margin. The other handle is if we change the second pole location, right? If we change the second pole location, the omega u corresponding to this will change. Also the phase also will change, right? So the overall phase margin will change, correct?
Yes sir.
Yeah. So what I want to what I want in this system is, I do not want to change the location of the second pole. I will only change the location. I will only change the phase margin by changing the gain of the system. Okay. Fine. So here I will just mention by changing the gain of the system, or by gain I mean DC gain. Okay. All right. So for so this is given. So try to do this question, okay? And for this, yeah, in the, it is very obvious in the second next question that for this new gain crossover frequency, what should be the gain of for the negative feedback system? So definitely they are asking that only. You do both the questions. So first you find
Yes
out
sir.
what happens, how much. First you find out if the phase margin is changed to 60 degrees, what is the gain crossover frequency, and for that gain crossover frequency or that phase margin, what should be the gain? It will not be 100, okay, it will has to be slightly lesser than that. So try to do it. And as I promised, I will conclude the session with this much only. I'll stop the session with this much only because there was nothing more to discuss. So I will meet you again in the next session on Tuesday. Okay, now the session will be on time and as planned. This session was conducted only because I missed the session earlier the last week. Okay, so now from now on,
Sir,
yeah,
sir, like in exams, they are going to ask numericals, right? So like objective and numericals, and some
I
of
have.
them are
Uh,
conceptual.
I don't think, I don't have an idea. Okay, that is something which you have to ask the course administrator. So I don't have
Okay,
an
sir.
idea about that. All
Okay.
right, so I'll meet you again in the next session on Tuesday. Okay, please join. Thank you very much for joining today. I'll again see you in the next session. Thank you.
Thank you, sir.